EC 111, UCSD, lecture 13, set 7. We're going to talk about signed operations on integers. So we talked about the signed numbers, and if we have a 2's complement number, if you want to negate the sign, we just complement and add 1, like I mentioned in the previous case. So this is basically what we do about negation. So what if, for example, we are trying to negate minus to the power n minus 1. So n to the power n minus 1 is 1000. So if it was a if you're trying to negate this, you're going to use it in the 2's complement, and this is this is what gives us that value. Remember that this range is not symmetric. As we mentioned, we have only one representation for the 0. So, if we have, say, 256 possible numbers, we can go up to minus 128, but on the positive side, we can go only to 127. So this is, this range is not symmetric. And, we have to make sure that the overflow doesn't occur because of this, because, we have this asymmetry. So we have to make sure that that doesn't exist. And, if you, in Verilog, you use the minus operator, the compiler is smart enough to know that you're negating a signed integer, and it's going to do the job correctly for you. The signed addition is pretty straightforward, the thing to remember is making sure that the sign bits are done correctly, and if you're having 2 n-bit numbers, then you add them up, you may get an overflow. If this overflow occurs, you need to make sure that you have 1 more bit for the addition. And this is consistent with unsigned addition. If you're adding 2 n-bit numbers, you need n plus 1 bit numbers to represent it correctly if you're not accounting for the overflow. So that's something that we need to make sure that we are aware of. So here, we are showing some examples of overflow case. Here we are adding 2 positive numbers, so the sign bits are 0, and we are adding them, so like again, the sign bit gets 0. If you're adding 2 1s, which are negative, and then we get an overflow, but this overflow we truncate, it doesn't really matter, because this is the number of sign number that matters to us. Now, if we get a number here like this, where we don't have a carry from before, then we get no overflow. But there are all these cases where we get this previous bit which has a carry here, and this could lead to a positive or a negative overflow. For example, here, what you see here, that if we add 72 and 105, even though these are 2 positive numbers, the sign bit here shows a negative number, which is wrong. And again, if you're adding 2 negative numbers here, because of this overflow problem, the sign bit is 0. So you have to be very careful for sign addition and the number of bits. Otherwise, you could easily get into this problem of overflow if we have the plus sign. So we need to make sure that if the result of sum is the same size as the operand, we get into this this scenario, which implicitly extends the sum. So in order to avoid that problem, Verilog has this function to help with this overflow. And in order to do subtraction, again, the whole point of doing 2's complement is that we can do subtractions effectively, as you probably have seen in your logic design course. So these are the same. Again, signed integers can be scaled similarly to unsigned integer. You could multiply by 2 to the power k, basically logic left shift, and then we could also truncate results using 2's complement rule. And dividing is logic right shift, and you discard the bits to the right. And this is, this may sometimes lead to losing the fraction for the divide, but this is one of the most simplest way to do a division by power of 2. Which, if you're only looking for approximate results. Of course, in real life, the division is, as we mentioned, is kind of more complicated than addition and multiplication, but it can also be done with a reasonably good accuracy. In the next set, we will be talking about fixed point numbers.